the output of MD5 hashing that message. The idea is, it may be hard, if a collision is found in SHA-1, chances are you're not going to find it in MD5. As the Zhu attack points out, apparently my slide, LaTeX didn't produce my slide correctly, but that should actually be 2 pipe symbols to denote concatenation down there. So the Zhu multi-collision attack shows that you can't actually cascade hash functions. You can't combine hash functions to get better results. So unless the first hash function is secure, then it's not going to be. Told you to turn that off. Okay, the long message attack, and it appears this slide has a few typos as well. The 2 to the 5 should actually be 2 to the 55. The long message attack, the way it works is you start with a long message, say 2 to the 55, 512-bit blocks. I don't know if there's any messages that are actually this size. This is such a huge message size that I would be surprised if, well, I don't believe any messages of this size actually exist. The attacker can violate the second preimage requirement, and that is he can find a second input that hashes to the output of this 255 block message if the padding scheme is done incorrectly. And this is why the padding scheme is of great importance with hash functions. So with this 2 to the 55 with this 2 to the 55 block message, there's 255 internal states. If you remember how hash functions were constructed, it operates on a block and then moves to the next block, etc., continually updating the IV. So after each block, there's an internal state of the hash function. So given 255 blocks, 2 to the 55 blocks, there's 2 to the 55 internal states. And because hash functions process messages sequentially, if an attacker can find a collision at any one of these 2 to the 55 blocks, if he has identical text on both messages after that, it's going to produce the same output. So he only needs to find a collision at any one of the intermediate states. So this gives him about 2 to the 55 targets. To accomplish this attack, he hashes all 2 to the 55 blocks, storing the intermediate states at each step. Then he searches among these intermediate states and looks for a collision with a shorter message. By the birthday paradox, you can expect to do this with about 2 to the n over 2 to the 55 work, which is much less than 2 to the n. In the case of SHA-1, it's about 2 to the 105 versus 2 to the 160. So you've significantly lowered the strength of SHA-1. This attack is stopped by both MD5 and SHA-1 by what's called Damgard-Merkle strengthening. And this is the reason for the input size limit. The way the padding works on most hash functions is, first you append a bit 1, then you append some necessary zeros up to 64 bits minus the block length minus 64 bits. Then you take a 64-bit representation of the original message size and finish the padding with that. And what this does is, it may collide up until the last block, but because the long message, which is 2 to the 55 blocks, and the short message are different sizes, they're going to have a different final padding. The message size is different. So it's not going to, yes?
Can I ask you a question about the slide that you had?
Sure. Yes.
When you talked about cascading hash functions,
yes.
Inside OpenBSD and the forestry, what they do there, I know they use a number of different hashing functions on whatever the call is depending on what you verify.
Right.
So would this mean that even if I verify this tarball with, say, MD5 and SHA-1, it's not necessarily more secure than just doing that?
Right, yes. You can't stick the MD5 hash on the end of the SHA-1 hash and expect there to be that much more security. It's actually not much more. Yes.
What did you say about finding collisions against 2 different encryption schemes?
What do you mean by 2 different encryption schemes?
Well, at least what he's saying is once you find collision in like SHA-1, and you're likely to find out what SHA-1. It doesn't say one about finding like MD5.
Well, yes, it does. The paper, he gives the evidence that if you use SHA-1 and MD5, it's actually not much more work than finding collisions in just SHA-1. And the original paper, I don't know, there's definitely not enough time to go through the attack right now, the full attack. I can give you a copy of the paper, but it essentially works with the SHA-1 attack, you have 2 to the 80 different messages. You've generated 2 to the 80 different messages for SHA-1 and found a collision, and it's likely that there's going to be a collision in there among MD5. So I can give you the paper if you wanted, or we can talk about it after the talk, but I was sort of conflicted when writing this talk about how much detail to get into. I think for anyone who's seriously interested in how the attacks actually work, a talk is no substitute for actually reading the papers. So this is sort of the high-level details, and if you're interested, I can talk to you more after the talk. We only get an hour, though. Okay. Second, preimages on n-bit hash functions for much less than 2 to the n work. This is actually an attack done by John Kelsey of NIST and Bruce Schneier. The attack extends the Zhu multi-collision in the long message attack to find collisions in the last block before the padding. So they've improved on the Zhu multi-collision finding, and they use this to create a long message attack such that the messages collide right before the padding. And as I said before, because you append the length of the original messages, you use the length of the original messages as the padding, messages of 2 different sizes can't collide. They then present an algorithm called expandable messages, which can take this shorter message and actually expand it into a message of the target size. Thus, when the padding is finally, when you compute the length at the end, it's of the same length, and thus you found a second input that produces the same hash as the long message, the target message. Their attack is impractical for a number of reasons. The total work to find these preimages is actually more than just finding a straight preimage, but it does I said that wrong. The total work for their entire attack is more than just finding a straight preimage, but it does show that once you've done the necessary pre-computation work, you can violate the second preimage principle. So the other reason why it's impractical is the same reason the long message attack is impractical, and that's simply because a 2 to the 55 blocks of 512 bits is such a large message. It's unlikely that any such message exists, or someone would actually try and hash it. I can't even imagine the computation time required to hash that. A few contrived examples of how these attacks actually affect security. In the case of a preimage or a second preimage, it should sort of be clear that if you can reverse the hash function or find a second input that produces the output, you can violate password schemes. With a lot of schemes, with a lot of applications, they use hash functions to store passwords. It's simply because there are collisions. Assuming they just do a straight hash of the password and they don't do anything special to thwart some of these attacks, there are multiple passwords that can get you on the system. So my user password, there's actually an infinite number of close to I'm going to round up to infinite because it's such a large number that it's 2 to the 64 minus 160, which is such a huge number. It's essentially infinite. Infinite is a good approximation for it. So because there are all these collisions, there's actually all these different passwords that will work on my user account. So you actually don't need to know my password. You can find some other passwords that also work with my username. The next example is probably the most contrived of them all. And that's, if you can find collisions, then you can forge digital signatures. And the way this works is the attacker starts off with two different messages. I will pay you $10 and you will pay me $100. If I want to use this attack against someone, they're probably not going to sign the message that says you will pay me $100. They're much more likely to sign the I will pay you $10 message. So he generates slight variations of this message, changing things like white space and punctuation and wording and whatnot. Obviously, if the message was longer, he would have a lot more play in the message and what he can change. I actually don't think you can change I will pay you $10 2 to the 80 different ways. So he generates slight variations of each message, changing things like wording, white space, etc. And by the birthday paradox, you can expect to find collisions in about 2 to the n over 2 operations. So in the case of SHA-1, well, MD5 would be a better example. In the case of MD5, after about 2 to the 64 work, which is on the edge of computing power right now, he can expect to find a collision. And the way digital signatures work is public key operations are pretty slow. So rather than sign massive documents, you compute a hash of the document and sign the hash. So these two hashes these two inputs hash to the same output. And if you agree to sign the document, this is I will pay you $10. I can remove the digital signature and put it on the message that says you will pay me $100, and then I can take you to court and show the judge that you signed this message. So, okay, yes.
Those messages, do they actually hash?
I'm sorry?
Those examples don't actually hash.
What do you mean they don't actually hash?
Those two messages hash the same thing.
Oh no, those don't. I'm saying. Yeah, no.
It's a lot of ASCII garbage.
Right, yeah. I mean, if you had a Word document, there's so much additional information in a Word document that you can change so much different thing, so many different properties and get all these different messages. Like I said, I don't think you could actually generate 2 to the 80 variations of that message. Okay, now some of the specific attacks. I should mention one of the problems with the recent attacks is they were done by teams of Chinese researchers, and there's huge translational issues. None of the papers have actually been translated to English, and our understanding is some of the results were actually presented at were submitted to previous conferences, but were rejected because the referees couldn't understand the English was so bad that they couldn't understand what the paper was saying. So, that's one of some of the attacks I can't cover so much detail because they haven't been translated and I don't read Chinese. So, what's that? Yes. So first I'm going to just talk briefly about these attacks because this is pretty much all the details known on them, but no one uses these, so they're not of that great importance. Havel was broken with only 64 hashes, so after you do SHA-1 64 times, Havel 64 times, you can find collisions. This can be done in probably under a minute on this laptop here. Collisions were found in RIPE-MD as well. They didn't give any. The original paper by the Chinese researchers, led by Wang, they only gave the collisions. They didn't actually give the work required to find them, except with the case of Havel. But you can verify that the inputs that they gave actually do produce the same output. So it's reasonable to believe that they were found with ease. Collisions in MD4. It should be noted that MD5 and SHA-1 are both improvements on MD4. There's changes that make MD5 and MD4 significantly stronger. MD5 and SHA-1 significantly stronger than MD4, but they are still based on the same initial design. Collisions have been found in MD4, and it's actually so easy to do that you don't even need a computer. You can do it with pen and paper. So I believe at the crypto conference, they actually did it on pen and paper and found collisions in MD4. Collisions have been found in SHA-0 and other pretty devastating attacks by Zhu and LEBM have found